get started here. I'll start recording. All right, so last week we kind of talked about this concept of where we're going to start integrating. And so we had this like scenario where we're going to integrate our way to the Superbowl, was just kind of the scenario that I set up on here. So I think we can all pretty much understand, like speed. If you're driving down the road at 50 miles an hour and you do that for a whole hour, then you're going to be, 50 miles further down the road after that hour has occurred. And so that's the idea of this again. So again, we're just kind of doing a little bit of review here. So we have the distance, or your current position, is we can measure between 2 points where we're at and where we're going to be at a future time, or where we were at a previous time. All right, and we can of course measure that in millimeters or meters or feet or miles, whatever unit you want to use to measure it. All right, but then when we take velocity, velocity is the amount of distance covered or going to be covered within a given time frame. So it's meters per second or miles per hour or whatever your units are, but it's a distance divided by a range of time. Okay, and the difference between velocity and speed is that speed is just the magnitude. This is how fast you're going. But velocity includes not only the magnitude, but the direction. All right, so for our example, we're assuming actually one direction. So we're just going in one direction, but we can like turn around or back up or whatever and go in the opposite direction. But we're not doing like a, north and east or something like that. We can go like north or south, but we're not going to be worrying about like east or west kind of directions. So it's just one dimensional. So we can, all right, and then so if we take that a step further, then acceleration is the change in velocity, and so that is a measure of distance of 2 points divided by time squared. All right, so, but as I previously mentioned, right, what we're really looking at doing, if we have the velocity, which is in miles per hour, and we calculate the area under the curve, that basically is what happens when we say, okay, I'm going 50 miles an hour, and I'm going to continue at a constant 50 miles an hour for a full hour. Then I've went 50 miles is how far I've traveled. Okay, so we're going to take the velocity and we're going to integrate it by calculating the area underneath the velocity curve. And that's going to give us the distance traveled then. All right, so we have to, of course, we have to have a starting point. Okay, so we've got to, I'll use the term later in the semester, I'll talk more about initial conditions. So I've got to have, where did I start at? What is my initial speed? I've got to know something about what's happening, and that something is usually what we call the initial condition or the starting point. Now, there are cases where we don't actually know the starting point, but we know that particular point in space. So we may actually have to go back the other way, and and sometimes maybe the solution is, okay, I know where I ended up, and I know that I have been traveling 50 miles an hour for 2 hours, so I know I've moved 100 miles, and so I can then determine where I started from. So sometimes we don't have the starting point, but we have some point in time and space that is our starting point for the simulation, at least, even though we may have to backtrack if we're looking for where the true starting point was or something along that line. And then we have to have our time step. All right. And then again, we're basically going to calculate the area under the curve. So if we look at calculating the area, all right, so you know here we're at this current location. So I kind of have this down here. I've got the current location, and I know how fast I'm going, then I can determine where I end up at. All right. And so again, this is a lot of this I talked about in the previous video, and I just kind of want to reiterate it. All right. So we have this idea of a time step. All right. So the time step is, this is where we're at now, and then after so much time, whatever that time step is, it could be 1 hour, it could be 5 minutes, it could be 1 second, it could be a millisecond. Usually we get to pick that time step to kind of match our system. But whatever this time step is, then we're going to determine where we're going to end up at. All right. And so we have starting time and effectively an ending time, or at least an intermediate ending. And so what we have then is, with this time step, we take multiple steps to get there. All right. We don't just say take one giant step. We take small steps to get there. And so what we do is, to keep track of these steps, we use a variable. Typically we use the variable k to keep track of these steps. It's kind of a traditional variable for calculating an integer value. All right, so these time steps are just like time step 1, time step 2, time step 3. And so then you have this k is your current time step, and then k plus 1 is where you're going to be when that next amount of time transpires. All right. Now we can kind of shift this. All right. So we can either say we're gonna guess, or not. It's not really a guess, but an estimate. We're going to estimate where we're going to be in this future time. Okay. So where are we going to be in a future time? And the way we do that is we take our current location, or our current value, and then we multiply it times the time step times the change. Now this is base times the height that we talked about. So this is our rectangle here. We can calculate the base times the height. All right. Now we can shift that and kind of do it the other way. We can call k is where we're going to be, and k minus 1 is where we're at now. So it doesn't matter which one that you do. You know, if you want to use a k plus 1 is equal to where you're at now plus your change, or you can do a k being, this is where I'm going to end up, this is the next time step, and this was where I was. All right. So this is, as long as you shift k everywhere, it doesn't matter which you do, whether you do the k plus 1 or k, and then here would be a k minus 1. So see here, this is where I'm going to be. This is where I'm at now. Or you could say, well, where am I now? And this is where I was one time step ago. All right. So you can do either one. I've kind of recently picked up doing the k instead of the k minus 1. So in my slides, I tend to have examples of, but just understand that all you're doing is shifting your time frame by one time step. And as long as you're consistent, it's not going to affect anything. All right, so here's an example where again we're on our way to the Super Bowl. Okay, and so we're starting at home, which means we're not moving. Our speed is 0. Our position is 0. We're going to increase our velocity to 20 miles per hour, but it's going to take us an hour to get up to that speed. All right, so we're not moving very fast here. Then we're going to stay at 20 miles per hour for 2 whole hours, and then we're going to speed up to 50 miles per hour. But it's going to take us an hour to change from 20 mile per hour to 30 mile per hour. And then we're going to slow back down. So we're going to slow our, I'm sorry, we're going to stay at that speed, 50 mile per hour for 1 hour. I don't know why I have an extra 1 there. And then we're going to slow down to a stop, but it's going to take us an hour to slow down. All right, so don't get in front of me because it takes me an hour to slow down. But this is just to make the code so that we can solve it very easily. Right, so here is a plot of that. I've got over here in the left is the MATLAB or Octave code. And then here is just plotting it. All right, so again, we can see we went and start down here at 0. Okay, so we're starting down here at 0 in the bottom left-hand corner. And then we are going up and to 20 mile per hour. We stay at 20 mile per hour for 2 hours. Then between hours 3 and 4, we're going from the 20 mile per hour speed up to the 50 mile per hour speed. Then we're going to stay at 50 miles per hour. And then we're going to slow down to a stop after 6 hours. So our total time is 6 hours, or from 0 to 6 hours. All right, so here is using the k+1 notation, and what I'm going to do is I'm going to use what again we referred to as the underestimation. So the underestimation uses, if we're doing a k+1, so we're going to determine where did we go, right? And what we're doing, let me flip back to this slide here a minute. Let me put this in Paint so I can do something with it. All right, so this was our thing, and what we're going to do is we're going to use k+1, okay? But in our k+1, we're going to use the velocity at point k. So if we look at this, here it is. All right, so when we look at this, then we're basically saying this is point K. This is point K. So this here point is k+1. And so given that, what we're going to do is we're going to calculate the area using our velocity. Remember, this blue is our velocity curve. So we're going to calculate the area underneath of this because we're just assuming the starting point. Here's my starting point, and here I am, and I'm going there. And so I'm at 0. This whole time I'm at 0. So what is my area? My area is simply 0. All right. And so, but then the next time I use this value and I travel for another hour and I calculate this area. And so now this area is 1 hour, right? It's 1 hour times 20 miles per hour. So now I've went 20. It's really hard to write with a mouse. All right. And then here now, I'm going 20 miles an hour. I do that for yet another hour. So this is another 20 miles that I traveled. So at this point, I have traveled a total of 40 miles. Right here, after 3 hours, I have traveled 40 miles. Now, remember, this is an estimation or approximation based on the fact that I'm assuming whatever speed I was when I started. So down here, I started at 0. So for that first hour, assuming I didn't do anything but sit there and twiddle my thumbs for an hour, I didn't move at all. Okay. Now, starting at this point right here, okay, so starting at this point, I'm going to travel for another hour, but I'm assuming that I haven't changed speed. Now remember, the blue line is showing the speed change that I'm actually doing. But in my approximation here, in the slide, where'd the slide go? In my approximation, I'm assuming the time at time k. And so that time is not changing. So I'm assuming that I'm just staying at a constant 20 miles an hour for this other hour. So now I'm assuming that I simply traveled another 20 miles. So I've traveled a total of 60 miles. This is my approximation that I'm doing. And again, we call this the under approximation because we're looking at where we're at and not looking at where we were in the future. Okay. This is also known as the Euler's approximation. It's actually probably better known as that. Now that I've done that, let me just kind of put a dashed line here. So now here at hour 4, I'm traveling at 50 miles an hour. So now I'm moving along here at 50 miles an hour. And so now I've went another 50 miles. And so therefore, 50 plus 60, so I've traveled 110 miles. Okay, so at this point, I've estimated that I've traveled 110 miles. I'm not saying that's what we actually did. I'm saying that's what my estimation using this Euler's approximation gets me, is the estimation of 110 miles. Now, right here at this time, I start slowing down. Right here, I'm slowing down to a stop. But I'm assuming that I stay at 50 miles an hour for this entire hour. I'm assuming that I have not changed my speed. So I'm actually predicting that I'm going to travel yet another 50 miles. So now I travel another 50 miles. So my total travel, this is the under approximation, was that I've traveled 160 miles. That's how far I've traveled. Okay. And again, this is just using this Euler approximation. Okay. Now, let me switch colors here or something. On the other hand, we could come over here . Let me just grab a screenshot of this here. Boy, screenshot software wants me to update. Sorry. So I'm just going to paste it. I don't want this whole thing here. All right, so what, again, this here was the under approximation, and the key here in this under approximation is the fact that I was using K. I was using K for my velocity. Okay, so I'm using K for my velocity. Now, if I do the over approximation, which again is also known as the backward Euler, the difference is right here, I put a K plus 1. So I'm going to look at I'm going to put a K plus 1, which is an over approximation. So what I'm doing now is when we start over here at the beginning, that's my current position. Okay, this is my current position. This is where I'm at. So if this is at time K, the first time this is time K, and time K plus 1. All right, that gives me the first one. So now I'm going to start here, but since I'm using the over approximation, I'm going to use K plus 1 for the velocity term. And so now I'm predicting that I traveled 20 miles in the first hour. See, with the under approximation, I assumed I traveled nothing in the first hour, but now I'm assuming that I've traveled 20 miles in that first hour. And so that's the over approximation. Now, then from here to here, again, I'm using this one over here because the next time this is K, the second time this one is K, and this is K plus 1. All right, so hour 2 is K plus 1 the next time. And so therefore, I'm still at 20, so I want another 20. So at this point, I'm predicting that I actually traveled 40. So I'm basically predicting that I traveled 40 in 2 hours, 40 miles. Okay. And then at hour 3 here, again, it's still at 20. So at this point, I'm predicting that I've traveled 60 miles in that amount of time. All right. So with the under approximation, at this point, I had estimated that I was only at 40 miles. Here, this is estimated that I've already traveled 60 miles. Okay. And then now I'm going to use this value up here at 4. So again, we've got 60 here. So now this is time K, and this over here at 4, it becomes K plus 1. So you see how the K and K plus 1 keeps shifting down the line. Okay, so the K and the K plus 1 keeps shifting. So here we have K and K plus 1, then it shifts and it becomes K and K plus 1, and then K and K plus 1, K and K plus 1, and so on. So it keeps shifting. All right, so at this point in time now, even though I'm right here, but I'm predicting, my next prediction is predicting that I'm already traveling 50 miles an hour. So I think that I've traveled 50. And so therefore, at this point in time, I assume I've already gone 110. All right. So after 4 hours, I've estimated that I've traveled 110 miles. Where with the underestimate, it took 5 hours for that estimate to get up to 110 miles. Okay. All right, so now I'm here. So this is time K, and this is time K plus 1 now. And So now I'm still at 50 miles per hour, so I'm predicting that I traveled another 50 miles. So at this point, I've predicted that I've traveled 160 miles after 5 hours. But at 6 hours, we look at 6 hours. At 6 hours, I'm at 0. So my last prediction is I didn't move anything. So in the under approximation, I estimate that I don't do anything for the first hour. In the over approximation, I'm estimating that I don't do anything during the last hour. Okay, now that's only because of this velocity, but so both of these, in this case, both predictions, the over and the under predictions are predicting that I've traveled 100 miles based on this blue velocity curve. Right? That doesn't mean that's exactly how much I did travel. Actually, in this case, if you do the math, that is, okay, because we know we can do that, right? Because here's a triangle, right? And so and this is a rectangle, this is a rectangle, this is a rectangle, or no, wait, sorry. This one's a trapezoid here. This one's a trapezoid. This is another rectangle. And then this is a triangle, right? And so we know we can calculate the true area. What is this area? This is where paint's fun, right? What is these areas? Okay, and so what we're doing is we're calculating this area, and we're adding them all together. So we're going to do in this area, then we're going to do this area, and we just add them and add them and add them till we get to our final answer. All right, so let's take a look here. So we know this is a triangle. So it's 1/2 times the base, which is 1, times the height, which is 20, which of course is 10. Okay, so my actual value that I've traveled right here, the true value that I actually traveled is 10. And then here, it's just a rectangle, so it's 1 times 20. Right? It's the base, which is 1 hour. The base is 1 hour, and the height is 20. So that means that I've traveled another 20 miles. Right? So I've traveled 10 and 20. So at this point, notice that the underestimate said I was at 20 at this point, but in reality, I'm actually at 30. So at this point in time here, let me use an arrow. So at this point, after 2 hours, I've actually traveled 30 miles. This is actual at this point. And then here now, this is another rectangle, 1 by 20. So at this point then, at this point right here, I've actually traveled 50 miles. Okay. So remember, the under approximation said I went 40 miles, and the over said I went 60, but the reality, I went 50. Okay, so they're both wrong, but I'm somewhere in between the two. All right, and then if we look at this one, I'm going to put it down here because it's up at the top of the screen there. But at this one here now, the actual, we went, this is a trapezoid, right? So it's 1/2 times the base, which is 1, times the first height, which is 20, plus the second height, which is 50, so that's 70. And so that is 35. So in reality, I traveled during this period of time, in reality, I traveled 35 miles. All right. So then at this point here, okay, so at this point, I've traveled a total of 85 miles. Okay. So 85 is how many I actually went. But then now, this is a big old rectangle here, right? Now we've got this huge rectangle here, right? Which is 50 times 1. So this is, or 1 times 50, either way you want to do it, right? So 1 times 50 means it's 50. Okay, I'm going to move this. This is the equation for the trapezoid. It should be here. This is the trapezoid right here. Can I rotate this a little bit? Well, I lost it. All right, so that was that area. So this is this one, and in this one I traveled another 50. Okay, so I've traveled another 50 right there. So I was at 85. So right here, I was at 85 over here. So now 85 plus 50 is 135. So I've traveled 135 after 5 hours. Now we've got another triangle over here, right? So the area of the triangle is 1/2 times the base times the height, which is 50. So that's equal to another 25. So this area is another 25. And so my true actual travel then, so my actual travel turns out to be, I was 135, and then I went another 25, so 160 miles. So my actual travel turned out to be exactly what both of these approximated. Okay. Unfortunately, it doesn't always work that way, but in this case, my over approximation and my under approximation match exactly. Okay. But the only reason that works so sweet is because I was using very nice straight triangles and rectangles and trapezoid sort of shapes. And so it works out in this case. All right. But it's nice when you do the first couple that you know the exact solution so that you can then put it inside the computer and get that approximation to match. All right. But what we're doing here in the code, all right, is, let's look at the code here again. Now, so the first thing we are doing here is right here. So right here, I'm doing the initial condition. So this is where I'm starting at. So this is the distance that I've traveled, and this is my time step, and I'm going to go for 6 time steps. Okay, so I'm going to go for 6 time steps, and what I'm going to do then is I'm going to calculate the new distance So I'm calculating my new distance, where I'm going to be based on my previous distance, here, where I am, and then the velocity, which is how fast I'm changing, times my time step. And so what I call the distance here is going to be my position after that. That's my distance traveled, okay, or my position where I'm at after that amount of time. Okay, and again, that was for the underestimation. So here I did the time shift. So I have the K over here on the left. So I have K over here on the left. And then I got a K minus 1 here and a K minus 1 here because I'm doing the underestimation. Okay, so I'm doing underestimation. It's the distance piece here. This is always the underestimate. But the velocity can either be the K minus 1, the previous value, or it could be the K value if I do the overestimate. All right, so here's the case where I'm doing the overestimate. So again, this is with the K plus 1 notation, K plus 1, K, and then K plus 1. And then I think the next slide, okay. So the next slide, I didn't show that shifted, okay, but we can shift that. If I put it back over here in Paint or something, I can shift that. All right, so here, again, I can shift this. If I take away the K plus 1s and just make those Ks, but then here I add in this K, instead of being a K, should be a K minus 1. All right. So again, you can either have K plus 1 let me do the whole for loop here to show you the difference. So if I'm doing K plus 1, all right, so if I'm doing K plus 1 here, then I'm going to have the number 6 here. So we have the number 6 here, and then I have a K plus 1, and this is for the overestimation, so this is a K plus 1. Now, if I wanted to change it and do the time shift, watch what happens. I'm going to take away the K plus 1, and I'm going to take away the 2. I'm going to take away this, and then I'm going to come up here. This now becomes 2 to 7. So see, this value here becomes 2 to 7. And then this value here becomes my K minus 1. All right, so we see like this changed, this changed, this changed, and this changed. Okay, so we took away the K plus 1s, They're gone. But now then we had to shift the k's. So the k's become a k minus 1. But then we also have to shift up here in our for loop. Instead of running 1 to 6, we have to run 2 to 7. See, because over here, this was k plus 1. The last value we had was 6. So k was equal to 6. 6 plus 1 is 7. So here now, we have to, since our last value is k, not k plus 1, we have to change our for loop. So our for loop is going to run for every case of k either 1 to 6 or 2 to 7. Okay. Now that's because we were only doing 6 iterations. All right. So what a for loop allows us to do is run through this. Right. And what we're doing is this was for 6 hours. So that was this, hour 1, hour 2, hour 3, hour 4, hour 5, and hour 6. That's why that for loop was running from 1 to 6. Okay, but there's actually 7 values because the first value you already had was 0. So you're starting at 0, and then 1, 2, 3, 4, 5, 6. So there's a total of 7. There's actually a total of 7 iterations that you do. So again, it doesn't matter which way, if you do the k plus 1 on the left side of the equal sign, or you simply do a k on the left side of the equal sign, but you've got to make that appropriate adjustment. All right, so when we plot these, the red line is the overestimate. Okay, this is the distance. The top line is the distance here. And the blue line is the underestimate. But if we actually plotted those values that I calculated, we can see that the true solution is somewhere in between these two. All right, so I've just got some code here, but I'm actually just going to do an example for you. All right, but so I'm going to do this again, but I'm actually going to pop over and do it for you here. Now, what I'm going to do, if I can, is I'm going to share this. Okay, share content. Let me save this, and I'm going to send it to you so you can have it open. You can kind of open it as a reference if you want. Oh, no. I just want to save the file. All right, so I'm just going to share this so you can kind of look at it there, as you want to or whatever. But what I've got here is I've got this scenario where very similar to what we just did, but a little more complex. And so what we're going to do is our velocity, we're starting from home. So speed is 0. We're going to speed up to 30 miles an hour in a single hour. We're going to stay at that speed for 30 miles excuse me, for 1 hour. We're going to stay at that speed for 1 hour. And then we're going to speed up to 70 miles an hour. So we're going to speed up to 70. We're going to slow down, and actually we're going to turn around and go the opposite direction. So we're actually going negative here. So we're going in the opposite direction. And then when we go in the opposite direction, you know, we're going to go in the opposite direction, but after that 4th hour, we're going to change directions again, and we're going to start going forward. Okay, and so remember, these are trapezoids. Actually, every one of these you can treat as a trapezoid. Okay, you can treat a triangle as a trapezoid because the area of a curve, or the area of a trapezoid, is 1/2 base times the height. All right, so 1/2 the base times the height. And so, you know, right here, the height is simply 0 at the beginning. So you can do that. You can actually treat these all as simply as trapezoids and calculate your travel. So the greens up here, these greens up here are showing you the how far you traveled. So this is the actual travel distance. So we're going from 15 to 45 to 95 to 120 and so on. So that green is actually showing you how far we've actually traveled. And so, and then I'm just kind of showing you, this is the area, right, of the triangle. This is the area of the rectangle here. This is the area of this trapezoid. I'm treating this as a trapezoid. I mean, it looks more like a triangle, but remember, a triangle is a trapezoid with one of the bases at a height of 0, but this is actually at -20, right? So right here at this point is -20. Right, so this right here is -20 down there. And so I'm treating this as a trapezoid, and I'm calculating the distance I traveled. So in red here are the distance that we've actually traveled. Okay, so during this time here, I've actually traveled positive 25 miles. I mean, I went positive for a while. All this time I'm going positive, but this amount of time right here, I'm going negative. So when you add up that I went positive for this distance, and then for this little bit of distance right here, I actually went negative. Right down in here, I went negative. And so I was going in the opposite direction. So that's why it's only 25 miles. And so we add these all up, and we come up with a solution that after 8 hours of travel time, I traveled 200 miles. That's the total distance that I traveled, right? And this is the true accurate solution. So the first thing we want to do is put this into our Octave. So we want to put this into Octave. Where's Octave? Or MATLAB if you're using MATLAB. Either one. All right. So I probably want to edit a new file. So actually, I like to just give the file a name right then. So let's see where I'm at. Okay. So I want to set my directory. Always set your directory first. Okay. So I'm going to set my directory. And I'm going to the sim directory, and then I have an Octave directory, and I have a Superbowl directory. All right, and so now what I'm going to do is I'm going to do the Superbowl I don't know. I need to name this a different example. This is, I'll just call it, today's 9/23. So I'll call it 2020-09-23. Okay. So what I'm going to do is I'm just going to type edit this, and it asks me to create this file and pops it open in the editor. Now, when they do this, they assume that you're creating a function. We'll talk about functions later, but I don't want a function, so I'm going to delete everything they give me here. And so then I'm just going to come in here. I'm going to start by putting my name. And then I'm going to put in the date. I really like to have the date there when you do it. And then if you modify it, it's nice to actually say modified at such and such a date. All right, so the first thing now is we want to clear. I want to clear all my variables. I'm going to clear the screen. I'm going to use at least one figure. And so I'm going to clear that. All right, and it's just always good to start off by cleaning things. If you know you're going to use a figure 2 also, then you could maybe go ahead and do that then. Then I'm going to put in my scenario. So I'm going to put these are just comments here. All right. So these are just comments. This is my scenario. I just talked about that. So we start from home. We speed up to 30 miles an hour. We stay at that speed for an hour. We speed up to 70 and so on. So that's just the scenario piece there. So now I'm going to create my time step. Okay. So my time step is simply 1 hour. Okay. My time step is simply 1 hour. And then my vector t, okay, is just going to be 0. And notice I'm going to jump down on the bottom line here, and I'm going to do my velocity. And what I'm going to do is I'm going to put these here together side by side so that as I go through it, I know I don't miss any. All right, so at time 0, my speed is 0. And then at time 1, my speed is 30 miles an hour. So after the first hour, right, I sped up. At hour 2, I am still at 30 miles an hour. I didn't change speed. At hour 3, I speed up to 70. All right, and you can put extra spaces in here just to make it look neater. It doesn't matter. Spaces don't make any difference. At hour 4, I slowed down and went the other direction to 20 mile an hour. All right, so at hour 4, I would actually slow down to 20 mile an hour. And then, you know, and we could even come up here and just count the hours, right? So this is hour 1, and this is hour 2, and this is hour 3, and this is hour 4. Did I mess up? So we stayed at 30, and we sped up to 70, and then we reversed direction. Okay, so I should have, I got my numbers wrong. This was hour 2, hour 3, hour 4, hour 5. So you just want to make sure this way you can keep track and make sure you don't mess up. Okay, so we're going to travel for 8 hours. All right, so then 1, 2, 3, 4. So hour 5, we speed back up to 70 mile an hour. And then at hour 6, I slow back down and turn around back in the other direction. So at the end of that, I'm going the other direction at 20 mile an hour. Then I'm going to speed back up to 40 mile an hour. And then I'm going to stop. All right, so you see how I just kind of walked through each one of these, and that gave me my my time vector and my velocity vector. In this case, I created the TS, but I wasn't really using it at the moment. All right, but I will use it later. All right, so now I'm going to then plot this. So I'm going to say subplot 2, 1, 2. So I want this on the bottom. I'm going to plot my time versus velocity. And so the X label is time in hours. And the Y label then is velocity, which is miles per hour. Okay. And so at this point, stop. Okay. Don't try to go too much. I've already done a whole bunch here. So go ahead and stop, hit play, execute this, run this, and make sure that it looks okay. So there is my velocity plot. Now I'm looking at it. It looks okay to me. The only thing is zero's not marked. So I just want to add a line here. So I'm going to turn my hold on to hold that figure. And then I'm going to plot from T1 to T end. You remember you need 2 points to plot a straight line. I want to plot a straight line at 0. 0, 0. So, and I'm going to make this just a black dotted line here just to mark it. So let me show you the figure before I hit play here. Here's the figure, and it looks okay, but 0 is over here, and it's kind of hard to see where 0's at. So by doing this, it marks and it shows you where I'm below 0. So where I'm below 0, I'm actually moving in the negative direction. Right, so over here at 4 hours and again at 6 hours, I'm actually moving backwards in time. And so I like to draw that line there. There is the grid function. We can come to the command window or whatever. I mean, and you can put the grid, you know, if you run grid, it puts lots of lines in there, and that's okay sometimes, but sometimes it seems a little busy with the grid. And so a lot of times I don't do the grid, but I just like to put some reference lines in there. All right, so back to my code now. Now I'm going to integrate. Okay, I'm going to integrate, and I'm going to integrate manually using trapezoids. All right, so I'm going to calculate the actual position here. Okay, so the actual position at time 0, which is the first one. Okay, so I'm going to create my k vector, k value. I'm going to say k is equal to 1, and so I'm going to say my actual position at k is equal to 0. Okay, because that's where I'm starting at. I'm starting at home, or I'm starting at 0. Now I'm going to say k is equal to k plus 1. Actually, let me double check. A lot of programs let you do k plus plus, but this one doesn't do it. Okay, I couldn't remember. Different programming languages give you other options, but all right, so k now is equal to k plus 1. So at this point, k is equal to 2. All right, and so then I'm going to say, well, then the actual position at k now is the actual position of k minus 1 plus the velocity, or plus the time step. Now this is going to be a trapezoid, so it's going to be the time step times the velocity of k minus 1 plus the velocity of k minus, or k divided by 2. All right, so this is a trapezoid here. Okay, I know I can use a trapezoid because I know it's nice straight lines. All right, so I can get the exact area of each of these using the trapezoid function. So now that I've done that, then I'm going to take this line here again, and this comes the k is equal to 3, and I'm just going to copy this. Okay, so k is equal to 3. Two, 3, k is equal to 4, k is equal to 5, k is equal to 6, k is equal to 7. Now we're going to 8. All right, we're up here, we're going to 8. So I need one more of these. K is equal to 8. All right, so now before I do anything else, I'm just going to run this and see if I get any error messages. So always come back to your command window and see if you're getting error messages, because if you mess up, you'll see error messages. So you always want to do just a few lines of code. I probably did too many in there, but a lot of it was copy and paste. All right, so it's not too bad if you're just copying and pasting, but you know, so there's a lot of lines here. And now the other thing is I'm going to run the whos command. Whos, and I want to make sure they're the same size, and they're not. So see, t is going 1 to 9. And so actually, yeah, that's right. So my k needs one more value. So I actually got to come back to my editor and do this one more time. When k is equal to 1, up here, when k is equal to 1, time is equal to 0. I should have put the time there. This is time equal 1. This is time equal 2 hours. This is time equal 3. Time equal to 4, and so on. Okay. So, and my time is running to 8. Time is equal to, remember, anything after percent sign is just a comment. So I'm just putting this here for your reference. T is equal to 6, and T is equal to 7. Now, this is just hard-coded. Normally, we don't want to do it this way. All right. Normally, we would not do it this way. I'm just showing you kind of, I need to put it in here. So this is our reference. This is our actual true solution. And so I want the true solution in here. And then we're going to do the Euler's method. All right. So, but this is the true solution. And I could have even automated this with a for loop, but I just wanted to do it the hard way the first time so you understand what it is that we're trying to do. All right, and so, but I need one more of these. I need k to go to 9, which would be time equal to 8. Okay. And so now, if I run this again, and I come over and run my whos command, I can see that they're all the same length. Remember, to plot something, they have to be the same length. So now that I know they're all the same length, I can plot my actual position. So I can come over here and I'm going to plot. Okay. So I'm going to plot position. So I need a subplot. I'm going to put this in the top plot. And I'm going to plot t comma actual position. And I'm going to make that, I don't know, I guess I'll make it green. And maybe I'll put a star at each point. And then now we really don't need an X label because both plots have the same time reference. So you don't need to do an X label again. It just kind of clutters it up. But we do need a Y label because this is the actual position, right, which is in miles. So we need to mark that. So I'm going to hit play. And now on my new graph, you see the dots are my actual positions. I actually wanted to do, though, I need a dash there to get the line also. So I want a line. Okay, so you can see here's my position. And I can't spell, I misspelled it. This is why you would put it in M files. So when you make a mistake, you just modify that and you rerun the entire code and end up with the whole thing re-executed with all corrections applied. So M files are just so nice. All right, so the green is the actual distance that we've traveled. So now what I'm going to do is I'm going to say, now we're going to use Euler's. Okay, so I'm going to use Euler's method, which is also known as the under approximation. We're going to use Euler's method here to hold on. Okay, let's see. I want to make sure I said that right. I get mixed up sometimes. Okay, Euler's I just okay. Now I got it in here. Where was it? I just want to make sure I said it right. Okay. Under approximation. Over is backwards. Euler is over. Okay, I just want to make sure I was saying that. So the under approximation, Euler's method is the under approximation, which is going to use the time at your known time at your previous position time. So what we have to do is I'm going to create a position, position underscore under, okay, to mark Euler's under approximation method. And we got to set it to 0, right? Because this is the initial condition. All right. And then what I'm going to do is I'm going to do a for loop. So the for loop is going to run through this every single time. In this case, we only have 9 Ks. All right. So we're going to run this for 9 Ks. But we already got the first one, so we only have to go from 2 to 9. However, we want to use our t vector so that we never have to worry about how many. I don't have to want to worry, do I have 9 or do I have 10 or do I have 11? I don't really want to worry about that. So I'm just going to come over here and I'm going to say for K2 equal 2 colon length of my time vector. All right, now for loops have to have an end. So you have to have an end here. What I like to do on my for loops is at the end, because they also use ends in while loops and if statements and things that we'll talk some about later. So I like to take whatever this is and I put a comment. Remember, anything to the right of the comment, it turns green, and it's just a comment. It doesn't do anything, but it tells me which end this one belongs to. All right, and so now what I'm going to do is I'm going to integrate the position. All right, because we already know the velocity. Okay, let me even write that here. We already know the velocity. Okay, and that'll come important next week when we do some other examples and we don't necessarily know the velocity or the derivative. Remember, the velocity is the derivative. Okay, so now all I do then is I'm going to say position. I'm going to say position under at time k is equal to position under at k minus 1 plus the time step. This is why I created the time step variable earlier, plus the time step times the velocity at k minus 1. This is the under approximation or Euler's method. So Euler's method, if we have this is k minus 1, the velocity is also k minus 1. That's Euler's method. Okay. Euler's also known as the under approx. All right, so now it's going to run through here. Let's just run this and see if I get any error messages. So I'm going to run this, and I'm popped to my command window, and I don't see error messages. So I'm going to go ahead and run the whos command here. And we see that they are all 1/9s. Okay, if I saw that like this position under was a 1/8 or something, then, you know, I kind of messed up my loop. I didn't do my loop enough times or something like that. So, all right, so now I'm going to go ahead and plot that. So I'm going to hold my subplot. So I'm going to hold the subplot here, and then I'm going to go ahead and plot t comma position under. All right, and I'm going to plot that in blue. Okay. And maybe I'll put a triangle there and a line. Okay, and then we can add the legend here. Now, if you need to do two single quotes or apostrophes here, so because, you know, technically this is Euler's, it's a possessive, so it needs an apostrophe. So when you need to do two apostrophes in text, you just like double it up, and it'll strip one of those out for you, and you'll have your so I'm going to do the legend there. Hit play, and then so you can see here's that. It's a perfectly straight line. What did I do? Velocity. Velocity. All right, I'm going to take away the semicolon here and see what's going on, because it seems like I must have made a mistake here. So I'm going to flip to my command window. Position under. Oh, I must have just messed up in the plot. What did I plot? Position. Oh, I'm plotting 1 point. That's it. I want to plot the entire vector. There we go. I was just trying to plot 1 point. That's why the plot wasn't moving. It was a straight line. All right, so now we can see that the green is the actual solution. So remember, green is the actual solution, but the blue is an approximate solution. And so with this approximate solution, you can see that actually when we turn around and go negative, here, remember that we used the positive value of 70 down here for that. And so it actually approximates that we went beyond at this point. So at this point right up here at 4 hours, so 4 hours and 6 hours, the Euler's approximation actually ended up doing an overestimate, which is kind of why I normally don't like that overestimate reference, because or underestimate reference, because this is technically the under in this case, and the under at hour 4 and hour 6 overestimates the distance traveled. All right, so the blue line is our estimated distance traveled. All right, so given that, we can then we can also do the overestimate. Okay, so what I'm going to do here is I'm going to right outside the for loop, I'm going to create an overestimate initial condition, and then I'm going to copy this and paste this, and notice I can do them both right here in the same loop. I just have to change my, and then over here when we're doing the overestimate, instead of doing k minus 1 for the velocity, we're doing a k. All right, and so remember, this is the backward Euler's. All right, so you notice how I can do them both in the exact same for loop there. It just takes one more line. And run it. Check your command window for errors. Okay, I removed that semicolon. I'm going to put that semicolon back in now. I don't need to look at it now. I figured out where my plot error was at. Okay, and so I'm going to plot the over. And the over, I'm going to make it red. And I put O's there, I guess. And so this is going to be backwards Euler. And I need to add the line there. So not a V, a dash. There we go. All right, so now you can see, again, the blue is the underestimate, but at hour 4 and hour 6, the underestimate actually goes and does an overestimate. And then the red is the backward Euler's, or the overestimate. And so it starts out on top, or overestimating, but at hour 4 and 6, you notice that it actually goes below. But notice that the true solution is in between the two. All right. So remember, the green is the true solution to this. Okay. But this is the Euler's approximation here. Now, the other thing to remember about this is the fact see, I was trying to do a screenshot there. I don't know if it didn't take it. Apparently it all right, so the numbers that we calculated are only valid at these points. Okay, so the calculations that we did are only valid at these points here. So we only have 9 points where we actually truly have values. All right. So all of this here, between here and here, and here and here, and here and here, these lines that we're looking at on the plot are just straight lines by the plot software. All right. So these things, these straight lines are just straight lines between the points. So the points are only the blue lines, right? And inside the blue squares, I mean. So the actual points that we have for any of our approximations or the true actual solution, okay, the actual solution may be something different here than what's plotted in the line, because we're just plotting a straight line between this point here and this point here. We're plotting a straight line, and that's it. All right. So so this is really poor resolution. So what we can do is we can plot more points. Now, the easiest way to get more points from what we already have is to use the linspace command. Now, before I do that, I want to just, let's say that we plot, or not plot, but I'm going to create a time vector t equals 0, colon 1, colon 2. I just want to do a little bit so I can keep it on the screen here. All right, so t is running from 0 to 2. So remember, the size of t is 3 elements. All right, we always have one extra element there. So now if I wanted to like double or half my time step, so now I'm going to come over here and I'm going to say t is equal to 0.5. Okay, so now notice here, right, we get 0, and then we get 0.5, and then we get a 1, and we get a 1.5. Now, let's take a look at the linspace. Linspace means linear space. So I'm going to create a linear space from my starting point, 0, to my ending point of 2, and I want 5 points. Because remember, what we got here? We got 5 points. So I want 5 points. All right, and so using linspace, I get these exact same match. But now let's say that I just want these last ones here. All right, so what I'm going to do then is I'm going to say 2 to end, and it just pulls off. It doesn't use the starting value, but it does have the ending value of 2. All right, and so this is basically what I'm going to do to increase my number of points inside of the thing. So I'm going to increase my resolution. Here, so remember we want a high res. I need to increase my velocity. All right, so I'm going to start with my velocity. So I'm going to create a time step high res. A lot of times I put a high res. So I'm going to create a high res time step of 10. All right, and then I'm going to, when I do my velocity now, I'm going to initialize my velocity high res. So I'm going to take my velocity high res and I'm going to initialize it at 0. Now remember, come back to this. See, we want to go from 0 to our next point, 0 to our next point, but then we want to drop this value. So I'm going to do the 2 to end. So, but remember, for my velocity, my first 2 points in velocity are 0 to 30. All right, and so I'm going to go linspace 0 to 30, and I don't want 10 points, because watch what happens if I do this. If I do 10 points, I get 0 to 30, but I only get 10 points. And so if I try to drop this one, I only have 9 points, not 10 points. So I actually have to do one extra. So I have to do 11 here. Now when I drop the first value, I'm going to have 10 values. All right, so if we look at the size of this, right, it's 11 values, but if we drop that last, or the first value, so if I say do this, but give me 2 through end, it drops the first value, and so I'm left with 10 elements. All right, so using that, I can come in here and I can actually create a little for loop. Okay, and I can say for 2 to the length of t, I'm going to create my velocity high res okay, that should be k equals. Now it's okay to reuse k because I used k here, but now I'm done with it. So once this for loop is done, I'm done with k. So I can create another for loop. It's okay to use k again. All right, as long as they're two separate loops. If I was doing a for loop inside of a for loop, which sometimes you need to do, then I have to pick a different variable. I can't use k again, and because it would try to be redefining it. But I'm going to say this k is equal to, okay, this is going to equal to my velocity high res of k minus 1. Actually, no, I don't even need to do that. I just need to do, what it's going to do is just keep adding to it here. So, and then linspace, okay. And what we're going to do is we're going to take this t high res, whatever this is, velocity of k minus 1, velocity of k, comma, and then this t high res, plus one more, because remember we're going to drop, and then we're going to drop the first value off of this, like that. And then we're just going to end this, and again I'm going to, oops. Put that in there. All right, so now this is going to give me a velocity of a lot of values. All right, so for every single value in velocity except the first one, I'm going to add 10 more. So remember my velocity, what did my velocity have here? Velocity had 9 elements. So when I'm done, I should, when I look at this now, the velocity high res should actually have 801. So I'm going to just throw right in here. You should indent inside your for loops. I didn't mention that before, but you should indent inside your for loops. It makes it much easier to read and to find the end. Okay, so indent your lines inside the for loop. But now right down here, I'm just going to run the whos command and look at my velocity. And then I'm going to look at my velocity high res, and I just want to see the size of them. And I'm just going to put this right in the code. So every time this runs and I look at my command window, I'll see that output, assuming it's running correctly. It's not here, though. I got a syntax error on line 73. So if I come back here, find line 73, I made it mad. I think I forgot my bracket. I forgot my square bracket over here, right? So always look at your command window, look for error messages. But now you can see, right, we had velocity. Velocity goes from 1 to 8. Or, well, I mean, it has, yeah, it's got It's got 9 values in it. Okay. And so now I've got 10 values between 0 and 30. And then I've got 10 values from here to here. And then I got 10 values from here to here. All right. So the next thing I want to do is I want to plot it. Because remember, this is what it should look like. It should look like this velocity curve here. It should look like this velocity curve. So what I'm going to do is I'm going to go ahead and plot on top of my velocity curve this high res velocity curve. So I'm going to recall my subplot 2, 1, 2. And I'm going to turn hold on. Actually, hold is already on because of the line. So I don't need that. But I'm going to plot my T high res. And then I'm going to plot my velocity high res. And I'm going to plot that with a cyan color. And it'll be right over top of the blue. And if I messed up, it won't be. Okay. And T high res is undefined. What did I call it? Oh, T. I didn't create T high res, I guess. T high res is equal to 0 colon time step high res and to the ending value of T, whatever that value was. Okay. So this value, what was that? T. See, if you use that notation, you don't have to worry about what the last value is. All right. But the last value is 8 because remember time is running for 8 hours. So we're going from 0 to 8 hours. But if I use this end notation, I don't have to remember that because I totally forgot. So I just put that in there. And so now, if I run this, look at my error. I don't see an error, but I don't see the plot either. I didn't see this plot down here. Where is that plot? T high res. Oh, I put the plot on top. I was looking at the bottom of the plot and it was on the top. Right here it is. Oh, I see it right there. You see it over there? Doesn't look right at all. But it was supposed to be on the second plot. Okay, but this T high res is not correct. This should be actually 1 over my time step. So this is this number here should be steps. So then this should be 1 divided by steps. Okay, and you kind of have to. So this is the steps between the known values. Okay, because we're basically interpolating here. Okay, we're interpolating in between there is what we're going to do to get more resolution. All right, 2, 1, 2. I still don't see it. See if I got an error message. T high res is undefined. I changed this to steps. All right, so remember, always look at your command window and look for error messages. Okay, always look at your command window and look for error messages. All right, so now you see this is no longer a dark blue, but it's got that cyan, that light cyan color on top of it. So notice it matches perfectly. If it doesn't match perfectly, then your high res velocity is not correct. So now what I'm going to do is I'm going to come up here to this Euler method stuff, and I'm going to come down for high res. And so I'm just going to put in like high res. So everywhere here, I'm just going to have high res. These were actually underscore high res. So to be consistent, I should put underscore high res. Always try to be consistent. Okay. And so this should be underscore high res. And this is underscore high res. And my T is underscore high res. And my velocity, I abbreviated it there because I added the high res. All right, so notice I have the exact same for loop I had up here, only I then added the high res. So this is a high res plot. And then I'm going to go ahead and hold or plot these. I'm going to go ahead and plot these. And so I need to add the high res on the plots. And what I'm going to do, instead of plotting blue there, I'm going to make this one cyan for blue, the light blue, and magenta for the for that. And so now I'm going to plot these, and I don't see the colors showing, so I got an error on line 86. So come back to line 86. T high res. Did I not? So I need to declare that. This should be TS underscore high res, which is equal to 1 over the steps. So then here, then I can't actually go back to T underscore high res. Oh, I forgot to change my subplot. So you can see there, right? It plotted it, but it forgot to change the subplot. And I'm also going to take off the symbols because notice here there's so many more points that you end up getting a really thick line if you plot all those. Remember, all those O's there are every point, because now I have 10 points between every hour, or from hour 2 to hour 3, there's 10 points, and so on. So, but I need to put my subplot in here. 2, 1, 1 to put it back on the top. All right, so now you can see there's the cyan color there and the magenta color are right there real close to the green. Remember, the green is the true solution, and cyan and the magenta are approximate solutions. But you see how much closer together they are than the red and the blue. All right, so we got those much closer together. And now the beauty of this now is I can increase the time step again. So let me make a copy of this. Take a screenshot of this so we can look at this in a minute here. So I'm going to, this is with a time step. This is with 10 steps each hour. And then I'm going to come over here. All I'm going to do is change the number 10 to a number 100. And I'm going to run it again. And you can see this is for time steps of 100. Okay. And you can see that they still vary from the actual solution, okay? But that the blue, the magenta and the cyan are right on top of each other. So, but to integrate, again, to integrate, what we're doing here is we're setting our initial condition. So this is our initial condition. We set our time vector. We build our time vector. Build our time vector. Then we set our initial condition. And then we do a for loop from k equal to the length of t, from k equal 2 to the length of t. Because we don't have to worry about 1. The reason we start at 2 here is because we already set our initial condition right before that. So this was k equal 1. This was k equal 1 right here. And so now we're just doing from 2 to the length. And then we have our velocity, high res. Actually, that's not the integration. That was just our linspace function there. But down here, we're setting our initial condition where k is equal to 1. And then we're going from k equal 2 to the length. And then we're taking the previous value, which we set outside the loop, the previous value is our initial condition. We're taking the previous value and we're adding to it this rectangle. This is a rectangle here, which is the base, which is the time step, times the velocity. And we're either using the previous known velocity or our next known velocity, one of the two. All right, so whether we're doing Eulers or backwards Eulers. Now, what we're going to find out next week is we're not going to know this one. We're not going to know this velocity, so we're going to have to use the forward Eulers most of the time. Okay. And so for the most of the time, we're using forward Eulers because we don't always know velocity ahead of time. Okay. All right, so and then again, we run this and double check your command window, make sure you have no errors in there. And then there's our plot and there's our solutions. Okay, so the red is the backward Eulers or over approximation with just a 1 hour time step. The magenta is the over approximation, but with a much smaller time step. It's a time step of 1/100th. So there's 100 steps between hour 2 to hour 3. There's 100 steps, and so it's a much closer approximation. The green is the actual value, but the green is only valid at the actual points: 1 hour, 2 hour, 3 hour, 4 hour. The green may or may not be accurate in between there, because we may not know that. In this case, since we were traveling at a constant acceleration, then it is actually accurate, but it may not always be accurate at those points. All right, so but that's how we do the approximation. So just a couple of things to keep in mind here, right? Distance is the integral or integration of velocity. Velocity is the integration of acceleration. The underestimation is Euler's method, and overestimation is backward Eulers. And we can do these time shifts, okay? Shifting k, you just need to do it everywhere. All right. And so basically our model is the derivative, or, you know, and then what we need to do to simulate is integrate.